Okay, let us go back to our topic. And the next thermodynamic potential is Helmholtz, and this is very, very important. Helmholtz free energy. Okay, so it is somehow written with F, I guess, for free. And it is the internal energy minus T of S. And you can very easily verify that the change in F is going to be minus P of dV minus S dt. And then we get something for pressure, which is delta F, delta V at constant T, and an expression for entropy, which is minus of del F by del T at V. Okay? So, we do a lot of isothermal processes, so temperature remains constant. So Helmholtz free energy is very useful for isothermal processes. And then, in that case, it's just the change in volume is really what's going to give you everything. Okay. And lastly, another useful one is Gibbs free energy. Gibbs is another big name in thermodynamics and also statistical mechanics, as we shall see. And Gibbs free energy is U not minus, but plus of ST. So over here, by doing minus of, what did we get? We got F to be a function of V and T, right? So over here, by adding ST, we got a function which is a function of V well, it's still a function of V and T, actually. Is that? I think I made a mistake, yeah. Yeah, it is a function, but it's just like that. It's a different, it's a different linear combination of these two things. Okay, yeah. No. It's not a function of V. It's a function of P. Yeah. Okay. What have I think I made a mistake here. Yes, the mistake is Gibbs is given by H minus TS. Sorry. Good thing I checked. Gibbs is given by H minus TS. Okay. And remember that H was what? It was a function of S and P, right? Right. And now that we are subtracting from it T times S, so D of G is D of H. D of H was T of ds plus V of dP. And now we have minus T of ds minus S of dt. So we get these guys canceling out. And therefore we have G is a function of T and P. Okay, so this was bullshit. Sorry. Excuse my French. Okay. And then, as usual, we can say, what is that gives us an expression for entropy, and so on and so forth. As well as an expression for the volume at constant temperature. Okay, so this is like all I have to say for today. But now let's have some questions, please. No questions?
So work is equal to minus PdV, right? Integration of
Right.
minus PdV. So
Yeah.
the F or Helmholtz free energy is like work, I assume.
Helmholtz free energy is like work. Let me see. Y. H is
Minus
well.
PdV.
They all Well, they all have. They all have. Yeah. They all have. They're all potentials, right? So they all have dimensions of energy. So there's always going to be, so it can be what you're saying is that the free energy can be changed by doing work on the system. Because energy, I mean, work is not energy. Work is a way of changing energy, right?
Yes, sir. Would you scroll down a bit?
Yeah.
Del F is equal to minus integration of V1 to V2 PdV. So this is work, right? I was
Right. This is in case of in case of a isothermal process. Yeah. So T is being held constant here. So T is being held constant. We do that a lot. We keep the temperature the same, but we change the volume and stuff like that of gases. So I guess chemists would know more about this than I would, because, or yeah. Any more questions?
Sir, I'll rewatch and ask if I have any.
Okay.
Same, sir. None so far. I'll just rewatch and like look through it again.
Okay. Well, this is like, there's a lot of it. I mean, the last few minutes I just gave you some information, right? Not a lot of thinking. It was just formulae, and hopefully in the future we'll get to more use of those formulae. But this is more of a stat mech class, not a thermodynamics class. So what day is now? We are fast approaching almost a 1 month mark, right? So I think pretty soon I will try to switch to stat mech. Okay. And I am working on the first assignment. It'll be assigned in a few days.
So there is a problem. So in Saturdays we have our tutorials, but those who are doing residential semester, they have an exam in Saturday, basically the whole day.
Okay, why did you? But then we can do the tutorial some other time. I mean,
Oh, okay.
Or you can, if you want, you can do the tutorial together at a separate time. We can have 2 sessions, okay?
Oh, okay, that would be nice.
Okay. Just for this once, because then, yeah. Any other questions?
Sir, I came like 15 minutes late, so I wonder if my attendance was safe.
Right. Let's see. It's Medad, right? Yeah.
Sir.
Okay. Yeah. Okay. It's fixed now. Did we have Nusaiba, or we don't have Nusaiba or Zakaria, Ushik Hassan? All right. Well, if you don't have any more questions, thank you very much, and have a good weekend. And we shall see some of you in the tutorial on Saturday, okay?
Okay,
Sure.
sir.
Okay,
Thank you, sir.
Thank
Thank you, sir.
you.
Thank you, sir. Bye.
I have one question about the example number 2.
Yeah.
When you said that there were no equilibrium states between the initial and final state, does that mean that if we suddenly like turned it off, then like it wouldn't stay in the middle, the states in the middle? Basically, it would. You couldn't pause it in the middle. Is basically like what I got from that. Is that right?
You could if you wanted to, but it's not necessary for you to get to the final state. So you're saying that what if I like stopped the gas from leaking halfway through?
Yeah, and then would it just stay still? I suppose in an equilibrium state it would just stay still, but
Well,
in a non-equilibrium,
then you will get to a different state, which is, and then after a while you will have an equilibrium, a different kind of state.
okay, I see.
I mean, you see what I mean? Is that that'll be a different state. You're right. And then you could talk about the entropy of that state and how to calculate that state. And, first of all, we won't know what the pressure of that state is, right? Because we know that the pressure is, the reason why we knew the pressure of the Joule expansion, the combination that we just we discussed, was that because we allowed the gas to equilibrate, and we know that the volume of the gas has doubled. Whereas the process that you are, describing is one where we have two systems really, where the pressure of the first two systems with volume V0, and neither of which pressure we know.
So basically, there are too many unknown variables.
Yeah, I mean, it's a very interesting question. I think there are some other, but yeah, I don't see how. So if you could tell me, like, if you could figure out a way in which you could figure out what the pressure, what the final state variable would be, in your scenario, then we could try to figure out, there would be a way to calculate the entropy.
Yeah, I haven't thought about it that far.
That's good. I mean, this is how you should, you should try to come up with a way of finessing your idea. There's another example in Blundell called the entropy of mixing, and it's basically about, you have two gases and you're mixing them.
I actually heard about that. I was watching the course by MIT before the semester started.
Yeah. So that's something that is where you have two gases and you allow them to mix. And then you calculate the entropy. So this seems more along what you're saying. There's also the idea of Maxwell's demon, which I want to discuss at some point, and which was a paradox until quantum mechanics came about.
Yeah, so the quantum information conservation.
Yeah,
right?
well, basically, quantum mechanics and the quantum information system, they basically, there is some, the demon will require some energy to do what he is doing. And if you take that into account, the total entropy does increase. That is
That was my prediction also, although I didn't have the quantum mechanics to justify it.
Yeah, because classically, the demon is just like, he is not part of the system, right? But
Basically, it's entangled, I guess, with
I
the
don't
system.
think. Yeah. Well, I don't know if entanglement is the right. Yeah, you're right. I mean, they're part of the same Hilbert. Yeah, you're right. They are.
The
Their Hilbert spaces are entangled. You're right.
the demon has to know which particle is coming and when to open the door. Then
Yeah.
that information
Yeah,
breaks the
exactly.
paradox.
Yeah.
I find
So,
Mech's demon extremely interesting.
yeah, I haven't really thought about it very deeply, but yeah, I have. But yeah, when we come to that, we'll try to go. We'll talk about some information theory as well. All right. Any more questions?
No, I think that's
No,
it for
sir.
me.
All right. Well, thank you so much, and I think Farhan, I owe you some explanations, so I will do that. Okay.
Yes, sir. Thank you, sir.
Okay.
Goodbye.
All right. See you guys. Bye.
Good evening, sir.